Hello to everyone. Welcome to the seminar of the Astronomy Department of IAG-USP. Thank you for your presence. Today we have the pleasure of having the presence of Dr. Khyati Malhan from Stockholm University in Sweden. Dr. Khyati, thank you for accepting our invitation. Let me talk a little bit about Khyati. He got his PhD in astrophysics from Strasbourg Observatory in France. Is it correct, the pronunciation? In 2018. And he currently works as a researcher at the Department of Physics of the Stockholm University. And he was recently awarded a prestigious Humboldt Fellowship and the IAU Gruber Research Grant. And he plans to start his new position at the Max Planck Institute in Heidelberg by November of this year. Khyati works in the domain of galactic dynamics and galactic archaeology. And his general interests are dark matter, galaxy formation, evolution, globular clusters, dwarf galaxies, and local group dynamics. And today, Dr. Khyati is going to present the seminar, the LMS-1 stream, a fossil remnant of the early formation of the Milky Way. Questions can be asked to Khyati after his presentation. If you are following the seminar on the YouTube channel, you can ask your question in the chat. If you are in Google Meet, just push the button of the hand to indicate you have a question. And before the seminar starts, I would like to ask everyone to please turn off your microphones and cameras. And Dr. Khyati, you can start your presentation whenever you are ready. Thank you.
Hello, could you please confirm that you can hear me well and also see the slide, the presentation?
Yes, it's perfect.
Yes, thank you so much. Hello, everyone. It's a real pleasure to be interacting with all of you today. First of all, thank you so much for the organizing committee for their kind invitation to give me this opportunity to talk about some of the recent work that I've been involved in. And in this respect, I'll be talking about the LMS-1 stellar stream that happens to be a fossil remnant of the early formation of our galaxy. Before starting the presentation, the slide that you're seeing is basically all the streams that our team has detected in the Gaia data using our stream finder software. I'm sorry. So each data point that you're seeing here on this slide is basically a Gaia star detected by the stream finder software. And the stars here are color coded by their distances. So the blue streams that you're seeing are closer to the sun, while the red streams like Palomar 5 or Orphan here you're seeing are color coded by red are further out into the halo or distant from us. And most of these streams are globular cluster streams. You cannot still see the LMS-1 stream here simply because I've not plotted it on this slide, but eventually in the subsequent slide, I'll show you the LMS-1 stream as well. So the outline of the presentation is as follows. First, I'll try to inspire the idea that why is it both important and also interesting to understand the formation of the Milky Way halo using stellar structures that are called stellar streams. Then after that, I'll move on to the detection of this very specific stream, the LMS-1 stream, that I've already said that we detected using the stream finder software in the Gaia early data release 3. And I'll also talk about some of the chemical properties and some of the dynamical properties of this LMS-1 stream. Eventually, I'll state some points in order to make the point that how LMS-1 stream, its detection and its properties advances our knowledge about the formation of our galaxy. And then finally, I'll present some concluding remarks, and the platform will be open for questions and discussions. Right. So to all the astronomers who are present in the audience, you could be interested in different domains of astronomy. You could be doing gamma ray physics, or you could be a dynamicist like myself, or you could be doing spectroscopy. But one of the very fundamental questions that most of us are interested most of the time is to understand how do galaxies form in our universe that is dominated by dark matter. And in this respect, LambdaCDM cosmological framework is quite useful as it suggests that galactic halos formed via accretion of multiple dark matter halos, the movie that you saw here. So there are lots of dark matter subhalos that merge together and form larger galactic halos. LambdaCDM model also predicts that very early in time, so at redshifts higher than 1.5, for example, the rate of accretion for Milky Way-like galaxies was much higher compared to recent times when the rate of accretion dropped down. So it's the stationary phase for the last 1.5 redshift units. So these are the predictions that we are getting from the LambdaCDM model. But generally, it is really hard to connect this prediction from the observation of galaxies from what we see. And the reason behind this problem is that what we observe are a sparse population of stars and gas and so on. So basically, just what we are able to see is just the luminous component of the universe. We cannot see dark matter because it's dark. So what we see, for instance, for the Milky Way or for any nearby galaxy, we'll see a host galaxy that's sitting in the center of the halo, and surrounded by sparsely population of stars in the halo, and then these satellite galaxies, these accumulation of stars that orbit around this host galaxy. So this is the observation that we get from our telescopes because we are seeing the luminous component. But what LambdaCDM model is telling us that the real picture is something like this. So in the underlying background, there's dark matter halos, dark matter clumps of dark matters all around. And then in those most massive dark matter halos is where the gas condensed and form stars and then eventually galaxies, what we are seeing. So it is this hierarchical growth of halos that is hidden inside the accretion of these dark matter halos that we want to understand in order to understand that how do galaxies, Milky Way-like galaxies, form in the dark matter dominated universe. And most of these dark matter halos that would have accreted early in time to the present day would not survive as these intact dwarf galaxies because they'll be tidally stripped by the host galaxy, and then the stars would be just distributed everywhere in the halo. And it is these stars that hold the information about the hierarchical growth of the halo, about the accretion history of the halo, that we are interested to understand. So once again, the LambdaCDM model is predicting that a majority of stars in the halo resulted from the accretion of several dwarf galaxies, but most of them are not intact anymore, at least not to the present day. And these infalling dwarf galaxies form stellar streams because of the tidal stripping of these satellite galaxies. They end up forming stellar streams, as you can see here in this simulation. And merely the observations of stellar streams, merely the presence of stellar stream provides testimony of this hierarchical growth history of halos, that indeed halos of Milky Way mass galaxies formed by the accretion of these dwarf galaxies. And it is due to this reason that stellar streams provide an excellent opportunity to constrain the hierarchical formation history of the Milky Way halo. And by constraining this accretion history, I mean we can literally constrain the number of accretions that took place, the number of dwarf galaxies that fell into the Milky Way halo, and also the phase space distribution of these accretions. And once we have this information from the observations, we can then compare it with the simulations from LambdaCDM framework or from any other framework from that matter. To talk a bit about stellar streams as well. So streams are formed when there is a satellite system and it's evolving around a host galaxy, and the stars begin to tidally strip from that satellite galaxy, and the overall structure looks a bit linear. So these streams closely delineate orbit in the galactic potential, as you can see in this simulation here. They're closely delineating the orbit. And it is primarily this property of streams, that they closely delineate orbits and the potential, is what makes them very interesting and very powerful probes of the hierarchical formation history of the halo, as I've already highlighted. Also to constrain the distribution of dark matter, both at large scale and small scales, to also study alternate theories of gravity, for instance, modified Newtonian dynamics, and so on. to constrain the figure of rotation of the halo. So for instance, cosmological simulations suggest that the dark matter halo actually has some sort of rotation in some direction. So we can really use streams to constrain that figure of rotation as well, to constrain the disequilibrium in the Milky Way halo, to constrain the sun's velocity in the galaxy, and to also constrain the total matter density in the galactic disk. So really, both in reality and also in theory, we can use streams for a variety of these questions. But the scope of today's presentation is just to highlight that how we can use streams to probe the hierarchical formation history of the halo, especially of the Milky Way halo. And this question is pretty interesting to answer using stellar streams, because once we have the orbit information of stream, we can literally trace that orbit backward in time and try and understand along what path did that accretion took place, along what path did those stars come into the Milky Way halo. So really revealing the dynamical evolution of those stars and the formation of the Milky Way. And stellar streams have been detected in external galaxies as well. I'll show you the detection of streams in the Milky Way, but they have also been detected in external galaxies. So here is the image of the Andromeda galaxy, and you can see lots of streams, a giant stream, and then another streams that have been detected in the Panda survey. Then further out, then more distant galaxies from us, you can see here, and you can see lots of streams and shells that have been detected in those external galaxies as well. And merely the fact that the presence of these streams, the observation of these streams are telling us that almost all of these galaxies are a result of this hierarchical accretion scenario, that some dwarf galaxy fell in and then populated the stellar halo around these galaxies. For the Milky Way, before Gaia, we already knew of several streams that were detected in the photometric surveys. You can see here. So these are the streams in the that were detected in the STSS survey, the famous Sagittarius stream, the Orphan stream that you can see here, and there were the Palomar 5 stream from the Palomar 5 globular cluster, and quite a few other streams that you can see here. And these are the streams detected in 2018 in the Dark Energy survey. But these surveys only provided the photometric information. Nevertheless, they provided us with this information of streams, suggesting that even the Milky Way halo was built by the accretion of several satellite systems. To talk about two of the most, so in the Milky Way, we know of about half a dozen of dwarf galaxy streams, so streams that were formed by dwarf galaxies. And two of these half a dozen of streams, two of them, the most prominent ones, are the Sagittarius stream and the Cetus stream. So the Sagittarius stream is the stream of the Sagittarius dwarf galaxy that you can see here in the galactocentric coordinates, and then the Cetus stream is the stream that you can see here. The common property of most of these dwarf galaxy streams is that they are dynamically young systems. So by dynamically young systems, I mean that they were only recently accreted into the Milky Way, in the last 3 to 6 gigayears ago or so. The main reason that we know that these are dynamically young systems is because these systems are phase-space coherent, which means that they did not receive enough time to completely phase mix. So had they been accreted very early on, they would have been more or less phase mixed into the halo. But they are not, suggests that they were only recently accreted. And also these streams have relatively large epicenters. So their galactic epicenters is beyond 35 to 40 kiloparsec, which means that if the Milky Way halo grew inside out, as suggested by the by the theories of galaxy formation, that any given halo grew inside out, the fact that these streams are surrounded in the outer halo means that they were accreted later in time, because the systems that were accreted very early in time must be concentrated in the very central regions. And the systems that are accreted late in time must be surrounded in the outer regions of the halo. So almost all the streams that we know of are dynamically young systems, and this raises an interesting question. And the question is that at present day, does the Milky Way contain signatures of dynamically old dwarf galaxy streams? So those dwarf galaxy streams that were accreted very early in time, so maybe 8 to 10 gigayears ago. And note that it is the knowledge of both the dynamically old streams and the new streams that can then provide us means to fully fledged constrain the chronological formation history of the Milky Way halo. starting from 10 to 12 gigayears till the present day. So that's the motive to detect these very dynamically old streams as well. And LMS-1 stream happens to be one of those dynamically old streams, as I will present after a few slides. And detection of these dynamically old streams is now relatively easier, especially with the Gaia data, because Gaia data is providing velocity of around 2 billion stars in our galaxy. So we can really use this added velocity information in order to pull out very faint stream systems as well from the field of stars, and in order to detect these dynamically old accreted systems. Now, just to talk a bit about how we can go about detecting streams in the ESA Gaia dataset. So just talk a bit about that. So Gaia provides, in addition to the photometry, Gaia provides 6D phase space information. So it provides the positions in the positions, the proper motions, which are basically the angular velocity, the two components of angular velocity, distances, but in the form of parallaxes. So what it really provides are parallaxes. Then the photometry and also radial velocity. So for most, and the most latest data release of Gaia, which is the early data release 3 dataset published on 3rd December 2020, it provides the 6D phase space information for only 7 million stars, for stars that are relatively bright. But for rest of the 1.8 billion stars, it only provides 5D astrometry. So this large chunk of data, 1.8 billion stars, do not have radial velocities. They only have 5D astrometry, 2D positions, 2D proper motions, and parallaxes. That's it for astrometry. And only a small fraction of these stars have the full 6D phase space information. This means that more than 99.5% of stars in the Gaia dataset has only 5D astrometry, no radial velocity. And most of these systems, most of these objects that have only 5D astrometry are halo stars, are distant stars. So in principle, we can use this smaller catalog of Gaia that also gives radial velocity information. So this 6D phase space catalog. And one simple way to find stream using this 6D phase space catalog of Gaia is to use this 6D phase space information and compute energy and action and angular momentum, and then plot them up, as you can see here from one of the studies. And the idea is pretty simple, is that objects that cluster together in the energy angular momentum space have very similar orbits, which means that they must have accreted inside the same system, and that's why even till present day, they have very similar orbits. So 6D Gaia catalog can be easily used to identify nearby streams, nearby accreted systems. But then this is again the limitation that we are only concentrated in the regions surrounding the solar neighborhood within 3 to 5 kiloparsec of the sun. And it's challenging to find systems that are further out into the halo. And it was with this mindset that I had started my PhD in Strasbourg in 2015, that how we can find streams in the 5D Gaia dataset that basically has most of the halo stars, but no radial velocity. And after a few experimentation with some of the catalogs, with some of the simulations, we realized that we really need a dedicated software to find stellar streams of the Milky Way in this 5D Gaia dataset. And then we came up with the algorithm that is called the stream finder algorithm, which is an automated algorithm that detects streams in the Gaia dataset. So what stream finder is basically doing is that it's integrating orbit. So for each star, remember each star has 5D astrometry, but no radial velocity. So for each star, stream finder integrates orbit in an assumed galactic potential model. And let's say your star happens to be a stream star. I should probably try and play this movie again. So for example, here your stream, let's say we are considering this star, and this star happens to be a stream star that you can see here. Then out of all the sample orbits, so we also sample within the uncertainties of the phase space, but especially in the radial velocity that we have no information about. So for instance, we sample thousands of orbits from minus escape velocity of the star to plus escape velocity, because that's the range that the star can take, the velocity that the star can take. And then the assumption is that if the considered star is a stream star, then at least one of these orbits would pass through its friends, would pass through the remaining members of the stream, as you can see here. And if so happens, then this particular star will basically get a very high likelihood value. So stars with more friends is a stream star and will get high likelihood value. But for the same star, if you happen to get a wrong radial velocity value in the sampling, then that orbit will not get a high likelihood value, but that's okay, at least one of the orbits did. And if your star is just a field star, doesn't happen to belong to any stream, then no matter what radial velocity sampling you use, it will not pass through any of the stars, and then this star will get a lower likelihood value. So essentially, at its heart, this is what the stream finder is doing, is that it's sampling orbit and then it's computing the log likelihood value for each star. So for each star, as I already said, that we end up integrating thousands of orbits, and then this process is iterated for all the Gaia stars in the halo that we consider. So the likelihood function in its simplest form looks something like this, that we have the stream term, the stream model, which is basically this orbit model that I showed you here, where we compute the likelihood value of stars relative to this integrated orbit. And then we have the contamination model of the galaxy that we build based on from the guide, using the Gaia data itself, to take into account the high density regions and the low density regions of the galaxy. This map that I'm showing you here is the most recent result from that we obtained by processing the Gaia early data release 3 using our stream finder software. Each star, each point that you're seeing here is a Gaia star that is color coded according to the proper motion value in the direction of galactic latitude. So basically, similar colors are basically marking that these found objects, these streams, are coherent in the velocity space. So maybe you can recognize some of these streams. So this is the famous GD1 stream that has been heavily studied. It's 100-degree long on the sky. The Silver stream happens to be very metal poor stream, likely from a globular cluster, has a metallicity of close to -3, which is very metal poor. There are lots of globular cluster streams that you can see, the Palomar 5 stream, the stream from M5, from M92, from NGC 288, and so on. This is the stream, the Fimbulthal stream over here is the stream from the famous Omega Cen cluster, which is the most massive globular cluster of the Milky Way. So in all, we have the stream finder has been successful in detecting lots of streams in the Gaia dataset. But here in this map, our aim was to find very narrow streams that could be coming from globular clusters. But we can change the parameters in the stream finder in order to find dwarf galaxy streams. So the parameters we'll choose is, for example, we'll ask the algorithm to find those streams that are very broad. So let's say 500 parsec in width, and have also large velocity dispersion. So let's say 5 kilometers per second. So if these values are small, then we'll end up finding narrow streams, globular cluster streams. But if we can change these values to find dwarf galaxy streams as well. And this is exactly what we did in this paper that I'll be now talking about. So we tuned the parameters of stream finder in order to detect the LMS-1 stream, which is a dwarf galaxy stream. So rest of the presentation, I'll be talking about the study that has now been accepted in the Astrophysical Journal. And I'll be talking about the detection of this LMS-1 stream, which is low mass stream, in the Gaia EDR3 using Stream Finder. I'll mention some of the characteristics, some of the very interesting characteristics of LMS-1 actually, both its chemistry and dynamics. I'll also talk about which of the globular clusters and streams of the Milky Way were possibly accreted inside the LMS-1's parent dwarf galaxy. And then finally, what we understand is that what role did LMS-1 really play in the formation of the Milky Way halo. Right. So this is the same map as I showed you before, but it can be dubbed as a dwarf galaxy stream map, where our aim was just to find dwarf galaxy streams. So the above map is color coded as per the proper motion in the galactic longitude direction. The lower map is color coded as in terms of proper motion, but in latitude direction. And you can see lots of streams here. So you can see part of Sagittarius stream. Here you can see the galactic anticenter stellar structures. You can see the previously known orphan streams. So these streams are previously known. But one of the most striking features in this map is this LMS-1 system, is this LMS-1 stream and some of the surrounding components that you can see here. We computed LMS-1's width to be 750 parsec, so it's quite wide. And it's at a heliocentric distance of 20 kiloparsec from us. So this part of LMS-1 lies basically beyond the bulge, because it's 20 kiloparsec from us, but in the direction of the galactic bulge. It is quite low in metallicity and has significant metallicity dispersion, as you can see here. And all of these, the large physical width and the metallicity dispersion is suggesting that LMS-1 is a dwarf galaxy stream. And for example, not a globular cluster stream, for example. And the metallicity of LMS-1 implies that its stellar mass is 10 to the 5 to 6 solar masses, which means that it's similar to, its progenitor was probably similar to the Draco dwarf galaxy, which is one of the famous satellite galaxies of the Milky Way, the Draco dwarf galaxy. We also found some of the stars towards the southern part of the sky that you can see over here. And these could be the southern agglomeration of stars, but belonging to the LMS-1 stream itself. And there are also some off-stream structures that you can see here. And the orbit of LMS-1 stream passes through these substructures as well, and also to some extent to the southern component of stars. And this suggests that it could be that the LMS-1 stream overall is surrounding the inner Milky Way halo, is surrounding the inner 20 kiloparsec of the Milky Way halo. But we lack radial velocity spectroscopic measurements of these stars over here, so it's hard to suggest this at this point. But the rest of the information does indicate that these stars are basically also the LMS-1 stars, but spectroscopic confirmation is required. Next, what we can do is we can compute the orbit of LMS-1, because as I previously said, that orbit of a dwarf galaxy stream can basically tell us the path along which that accretion could have taken place. So we computed orbit of LMS-1. So we use this part of the stream, and because we also have its spectroscopic observation, so we have its radial velocity that's shown here. So this is the position. These are the parallaxes of the stars from Gaia. These are the prop motions or angular velocity from Gaia. And because Gaia lacks radial velocity, we had to rely on other public spectroscopic surveys to get radial velocities for these stars. And then we computed the orbit for LMS-1. And what this orbit is telling us is that LMS-1 has quite low eccentricity of 0.2, which means LMS-1 lies along a nearly circular orbit. It is moving along a prograde direction, so its moving component lies in the direction of the rotating disk, so it's prograde rotation. Its epicenter is quite small, about 16 kiloparsec, and its pericenter is 10 kiloparsec. Now, these two properties of LMS-1, its low eccentricity and its low epicenter, it's quite surprising, because all of the intact dwarf galaxies of the Milky Way and also all of the other dwarf galaxy streams of the Milky Way have very high eccentricity, which means they are on radial orbits and have quite large epicenters of about 35 to 40 kiloparsec. So this makes LMS-1 dwarf galaxy streams quite interesting, because its orbit strikingly stands out from the other dwarf galaxy streams and also dwarf galaxies. So there are two ways to explain this very interesting and peculiar orbital property of LMS-1. One is that the reason that LMS-1 has a circular orbit could be that its orbit got circularized if the progenitor, if the parent LMS-1 galaxy was quite massive and it underwent some dynamical friction. So if the massive system can go under dynamical friction in the galaxy, and that can circularize the orbit, and maybe that's why it has such a low eccentricity. It lies along a nearly circular orbit. And the fact that LMS-1 has a very low epicenter could be highlighting that the parent LMS-1 galaxy accreted very early on when the Milky Way was smaller, and that's why it's contained in towards the very central regions of the halo, unlike other dwarf galaxy streams like Sagittarius and Cetus that occupy the outer halo and were only recently accreted. So LMS-1 could have been accreted very early on in that sense. And so this is what these orbital properties are suggesting, that LMS-1 is an early accretion. We also compared the orbits of LMS-1 with two of the globular clusters, NGC 5024 and 5053, because we want to understand that which other globular clusters of the Milky Way could have come inside the parent LMS-1 galaxy. And here are I'm comparing the orbits of these two globular clusters in yellow and orange orbit with the orbit of LMS-1 that you can see here. So these two orbits of these two globular clusters are quite similar to the orbit of LMS-1. And also the metallicities of these two globular clusters are similar to the median metallicity of LMS-1. I'm showing you two other plots in this metallicity distribution function. I'm showing you two other points in this metallicity distribution function for Palomar 5 and for Indus. And I'll talk about these in a minute, but right now we are concentrating on 5024 and 5053. So this suggests the similarity in the orbit of these two globular clusters and also in the metallicity is implying that these two globular clusters were accreted inside the LMS-1 parent galaxy, and that's why they have very similar orbits and metallicity as that of LMS-1. So the fact that we could find these two globular clusters that were possibly accreted inside LMS-1 motivated us to basically analyze all the globular clusters of the Milky Way and some of the other stellar streams of the Milky Way and examine whether any of those could have accreted inside the parent LMS-1 galaxy. And one best ways to do this is to compare the distribution of LMS-1 with that of observed globular cluster of the Milky Way in the energy action plot that you can see here. So the idea is pretty simple, is that in these plots, systems or objects that are clustered very close to each other would have accreted inside the same parent galaxy, and that's why they have similar orbits, and hence they would cluster close to each other in the space. So this is the action diamond space. The y-axis is the subtraction of the z component of action and the radial component of action, and the x-axis at some level is telling us, giving us the z component of angular momentum information. And this is the z component of angular momentum versus the energy diagram. So in this plot, the objects that lie on the left hand side have motion in the direction of the disk. The objects that lie on the right hand side have opposite motion. But the main idea is that objects that cluster together in this space must have accreted inside similar parent galaxy. That's the main idea that is generally used. And now here, I'm comparing the simulation of LMS-1 with the globular cluster. So each star that you're seeing, so the blue points that you're seeing here are LMS-1 simulation. The gray stars that you're seeing are basically 150 globular clusters of the Milky Way. This pink point here is the Indus stream, which is one of the other streams of the Milky Way, the Indus stream. Here I'm highlighting the phase space, the region that the Cetus stream occupies, and this is to highlight the region that the Sagittarius stream occupies, is what is shown by these ellipses. And as you can see, that the energy action and also other orbital properties of NGC 5024, NGC 5053, and the Indus stream overlap with the distribution of LMS-1 in this energy action space. Also, the Palomar 5 cluster, globular cluster, also overlaps in this space. That sort of suggests that it could be that Palomar 5 also came inside the parent LMS-1 galaxy. In addition to comparing these systems in the energy action space, we can also compare their metallicities, that is shown here, and also their stellar population in terms of the color magnitude diagram. So here I'm comparing the metallicities of these four objects, Palomar 5, Indus, 5024, and 5053 with the distribution of LMS-1 in metallicity. And here I'm comparing the two globular clusters with LMS-1 in blue and the Indus in magenta and LMS-1 in blue again. And this comparison of stellar population, of metallicity, and of energy action suggests that NGC 5024, NGC 5053, these two globular clusters, and also the Indus stream were accreted inside the parent LMS-1 galaxy because they behave quite similarly in the schemodynamical space. And it could also be that Palomar 5 also accreted inside the parent LMS-1 because it lies within the range of this metallicity of LMS-1, although its color magnitude diagram is quite different, so it's a tentative. It's a bit hard to conclude the same result for Palomar 5, but at least these three systems came inside the LMS-1 parent galaxy as suggested by these comparisons. So now I'm moving towards the conclusion of the presentation. So we have these three dwarf galaxy streams. And one common thing between these three prominent dwarf galaxy streams, the Sagittarius dwarf galaxy stream, the Cetus dwarf galaxy stream, and the LMS-1 dwarf galaxy stream, is that they lie along polar orbit. So their structure is such that they are sort of perpendicular to the galactic disk. So for example, the Sagittarius inclination is 76 degree to the plane of the galaxy. So if this is 90 degree, then you're dead on perpendicular to the galactic disk. So this is 76 degrees, Cetus is inclined at 60 degrees, and LMS-1 is inclined at 75 degrees. So these three prominent dwarf galaxy streams also happen to be quite polar in their orbit. Sagittarius spans the outer galactic halo, ranging from 15 to 100 kiloparsec of the Milky Way. Cetus spans the intermediate galactic halo, 24 to 36 kiloparsec or so. But LMS-1 spans the very inner galactic halo region, so 10 to 20 kiloparsec in distance from the center of the galaxy. As we understand, Sagittarius contributed 8 to 10 globular clusters to the Milky Way, with M54 globular cluster being its nuclear star cluster, sitting at the very center of the Sagittarius dwarf galaxy. Cetus contributed at least one globular cluster to the Milky Way, NGC 5824. And LMS-1, as we realized from the study, contributed at least two globular clusters plus one stream to the Milky Way. And NGC 5053 was possibly originated from the very central regions of the LMS-1 dwarf galaxy. But Sagittarius dwarf galaxy is a dynamically young system that was quite recently accreted. However, on the other hand, LMS-1 is a dynamically old system that was accreted very early on. So in this sense, so what I'm trying to say through this information is that in this way, by combining the information of the old accreted streams, of dynamically old streams and dynamically young streams, we can put this in some chronological perspective, and perhaps we can say that maybe LMS-1 accreted early because it's surrounding the inner halo, and then Cetus came in after the LMS-1 accretion, and that's why it surrounds the intermediate halo. And finally, very recently, the Sagittarius dwarf galaxy came in, and it's surrounding the outer halo. So these are the sort of questions that we can try and address and form a picture of how our galaxy would have shaped by the accretion of these dwarf galaxies. One of the questions that I'm currently trying to understand in my mind, just trying to understand, is that how common are such polar dwarf galaxy streams in Milky Way mass galaxies as per cosmological simulations? And the reason that I'm trying to understand this, it's just a question in my mind. And the reason that I think that it could be an interesting question is that if cosmological, because this thing that these three dwarf galaxy streams are on quite polar orbits, it's something new to me. To me, at least, this is something that I didn't predict or I didn't hope that we would find. But the fact that the three prominent dwarf galaxy streams of Milky Way are on polar orbits, maybe we can try and study this even with cosmological simulations, because in cosmological simulations, if we find that such polar dwarf galaxy streams are common in Milky Way mass galaxies, then would that mean that polar streams are the major source of stellar population in the halos of Milky Way mass galaxies? That is it really that we should generally expect dwarf galaxy streams to be in this polar configuration? But if cosmological simulations suggest that no, such dwarf galaxy streams on polar orbits are uncommon phenomenon, then is it that our Milky Way galaxy is special in some way, that most of the prominent dwarf galaxy streams are lining up along this polar orbit? So I think this is something would be interesting to think about in general. And with that, I'll just quickly summarize my results, the three main points. It is that what I've tried to say is that stellar streams provide direct evidence of the hierarchical formation of the Milky Way halo, also of other galaxies. But the interesting thing about doing this in Milky Way is that we have the velocity information with Gaia, and also spectroscopy of many of these systems. So trying to understand the question of accretion history of the Milky Way halo using stellar streams is both interesting and important. And in this respect, the LMS-1 system happens to be quite an interesting stellar stream, primarily because it has a very unique orbit, the polar configuration, the low eccentricity, and the low epicentric distances as well. And all of these sort of indicate that the parent LMS-1 galaxy was accreted very early in time, maybe 8 to 10 gigayears ago. The halo mass of the system was of the order of 10 to the 9 to 10 solar masses, and the stellar mass was 10 to the 5 to 6 solar masses. So more or less like ranging between the Draco dwarf galaxy or the Sagittarius dwarf galaxy. We find also evidence that LMS-1 is completely wrapped around the inner galactic halo. That would make it the second stream that completely wraps around the inner galactic halo after the Sagittarius stream. It is also the case to some extent with the Cetus stream, but we have this another stream that also wraps around the inner galactic halo. And therefore, LMS-1 could also be a very powerful probe of the dark matter distribution of the in the Milky Way and the flattening of the dark matter halo in the Milky Way. We also understand from the study that LMS-1 possibly brought in at least two globular clusters, NGC 5024, 5053, and another stellar stream Indus, and also possibly Palomar 5, a globular cluster. And all of these properties and this characterization of LMS-1 makes it a very important fossil remnant of the early formation of our galaxy. And it would be interesting to put this LMS-1 system in perspective with the other known accretions of the Milky Way in order to understand the full chronological formation history of our galaxy. And with that, I thank you very much for your attention. Thank you.
Thank you, Khyati. Very interesting and clear presentation. Now we have time for questions. I will start with a question from Professor Hélio Jacques Rocha Pinto, and he wrote in our channel on YouTube. How do you decide on which solutions coming from the algorithm are not real physical alignments? And do you use threshold statistics coming from random simulations?
Oh, could you please repeat the first part?
Yes. How do you decide on which solutions coming from the algorithm are not real physical alignments? And he completes the question: do you use threshold statistics coming from random simulations?
Do you mean the first part of the question, that how do we know that these are polar orbits? I'm not sure if I understand.
Solutions. How do you decide on which solutions coming from the algorithm are not physical alignments?
Coming from? I'm sorry, coming from?
From the algorithm.
From the algorithm? I understand. The stream finder algorithm. So yes, so that's a good point. So for example, maybe Professor was referring to this particular map. So for example, we do see lots of streams over here, but some of them are probably do not seem very convincing at this point. Maybe it's the tiny ones, the C11, for example, or C13, or maybe these tiny streams. So you're true in suggesting that maybe these are not physical, maybe these are just I don't know, false positives or something. But then what we can do is that with Gaia, we do not have radial velocity, because if we have radial velocity, then what we can do is that we can plot all these stars in the 6D phase space and then see if they really look streamy, like do they really look that they have some sort of orbit nature, if they're linear structures. So what we can do is that, because with Gaia, we do not have radial velocity for most of these stars, we can go for spectroscopic observations. We can get radial velocities of these stars. We can plot them up, and then we can see if they form some sort of linear structure also in the radial velocity space. Because by construction, because these stars are processed by Stream Finder, of course they do look streamy in the position space, in the distance space, and also in the prop motion space, so in the 5D phase space. But to also confirm that in the radial velocity space, we need radial velocities, and once we have that, we can confirm it. But having said that, for most of these stars, for most of these streams that you can see here, we do have radial velocities from previous studies and also from our own spectroscopic campaign. And for most of these streams, they do look real even after, once we plot them up using the radial velocity, they do look streamy. So that's one way to confirm if the algorithm, what algorithm is giving, is a physical solution or not. But most of these structures are in fact physical solution. They do look streaming. They are streams. What was the second part of the same question, please?
Thanks, Richard. Sorry. If you use some threshold statistics coming from random simulations in order to help the algorithm to decide if the alignments are real or not.
No, we don't do that because, I mean, so our galaxy, it's quite complex, right? And we do have some simulation data that, so I mean, so one of the things that we could have done is, for example, we could have used some of the existing simulations and use those as the contamination model, because then that would give us some idea that if what we are finding as these linear structures are real or not. But we instead chose to use the Gaia data itself, because the Gaia data is much more complex than any of the existing simulations. Also, the real data will have those sort of correlations and everything that maybe some of the simulations do not. So we do not, so these detections are not based on any do not assume any simulations for these detections, but most of these detections are real because they are also spectroscopically confirmed. Yes.
Thanks. Now the next question by Laerti. Please, Laerti.
Hi, very nice talk. Huh? Congratulations. My question is, do you know whether there are any evidence for dark matter in the streams themselves?
Whether there are dark matter in these streams? Is that your, I'm sorry, is that your question? Whether there are dark matter?
Yes.
Okay.
Because if they come from a galaxy has also dark matter, so...
True.
But since you are modeling, maybe you have a hint about that.
Yes, so you're right in that sense. Maybe I can show you a plot that I didn't show in the presentation. So here is so in gray, what you're seeing is the simulation of LMS-1 that I ran. So these red stars and these substructures and the southern agglomeration of stars you're seeing here is the Gaia data. But I ran a simulation just to examine that how does the simulation compare with the observations in the 6D phase space that you're seeing here. So in this sense, we do have a prediction of dark matter, that's how dark matter would be distributed along the stellar component of the LMS-1 stream. So yes, so here is the prediction, but then the question is that how can we possibly test? I mean, how can we possibly detect this dark matter, right? So all of this could be dark matter. There could be dark matter inside these stars as well, sure. But I mean, so that's why, I mean, one of the things we can do is, for instance, is that we can measure the velocity dispersion of the stream. That can help us. So the velocity dispersion of the stream that we do compute, which is very large, can give us estimate of the dynamical mass of the progenitor of the parent galaxy, and then compare that dynamical mass with the stellar mass. And if there's a huge difference, then that's basically telling us that yes, indeed, there should be dark matter around this LMS-1. But yes, so I'm not sure if I answer your question.
Oh, yeah.
But this is a
very
prediction.
good answer, by the way. Thank you.
Welcome.
Now, Betty, please.
Oh, hi. Very interesting talk. Thanks. I have two questions. One regard the dark matter in the core halo of our galaxy, and the other question regards the interaction between the LMS stream and the gas distribution of our own galaxy. So let me go to the question on the dark matter. So we see that the LMS has the circular orbit around the center of our galaxy, or around this halo, right? Can we conclude that this empty halo, or I mean, because this circular orbit is a perfect one. It's a very the orbit traces the circular shape around our own galaxy center within 20 kiloparsec scale or so. Isn't that so? So can we say that this shapes the let's say the form or the format of our own dark matter, of the Milky Way dark matter core halo? Can we say so?
Oh, you're saying that, is it that the dark matter that is surrounding the
Yes,
LMS-1
yes.
is the only dark matter that's present there?
Essentially, yes. This is my question. Can we say so, that this shapes the circular orbit, shapes the, let's halo of our own galaxy, because its extension is the diameter, the radius of this orbital shape is 20 kiloparsecs, isn't that so?
Right. So so the thing, right, I mean, I do understand your question, but I think I would be I mean, I would be a little careful with that understanding, and the reason is that, so I think there is more dark matter in the central regions, especially within 20 kiloparsec of the galaxy, than than just coming from LMS-1. It's because, I mean, even before the LMS-1 would have accreted into the Milky Way, there would have been dark matter in the central regions. Plus,
no, I'm not saying that this would be the dark matter coming from the stream. I would say that this is, let's say, it shapes, it traces, the orbit is able to trace the inner core of the dark matter of our own galaxy, the dark matter halo of our own galaxy.
True. So, I mean, if I understand the question this time correctly, yes, exactly. So the way that LMS-1 is distributed in the galaxy is I mean, it is sensitive to the fact that how the dark matter in the Milky Way is otherwise distributed within the 20 kiloparsec region.
Exactly.
So yes, yes. So in that sense that, yes, LMS-1, the phase space distribution of the LMS-1 would be quite useful to constrain the shape of the dark matter halo within 20 kiloparsec.
Yeah, this is my question. This is my point. If this really makes sense, right? This correlation.
And especially, I mean, to that degree, especially
because all these streams, are, you know, they have complex orbits around the galaxy center of our own galaxy, and in particular, the LMS within this 20 kiloparsec radius, it could influence, its gravitational field could influence our own gravitational field in the center of the galaxy itself, and therefore it could disturb the distribution of gas in the galactic disk in our own galaxy, right? And in this sense, it could have some, you know, so it affects the distribution, breaks the hydrostatic equilibrium, all this stuff, and then it might affect the formation of these high velocity clouds that go above the disk of our own galaxy, and whose origin is still, you know, controversial, because it may be associated to supernova explosions or not. Some of these streams of high velocity gas coming out from the galaxy disk are really high, so high that it's hard to explain how they are associated really to galactic fountains driven by supernova remnants. So could the gravitational field of these streams affect the gas distribution in such a way that they could also be responsible for some of these high velocity clouds, for instance? In other words, I would like to know if you have some studies on this, if you have performed some studies on this correlation between gas distribution in our own galaxy and the streams.
So first of all, no, I have not studied any correlation between streams and gas in the Milky Way, or how the dynamical evolution of stream can perturb the distribution of gas. I personally have not done that. Secondly, So let me say a few things, and maybe then I can ask you if I have answered your question. So one way to check this for LMS-1, for example, I mean, let's say this is LMS-1, right? It is not, but let's say
Right.
you're saying this LMS-1. So one way to do this would be to take a cosmological simulation, start with some smaller value of Milky Way that you think it was 10 giga years ago, when the universe was 4 giga years old. And you start with that. I mean, right now we think that the Milky Way's mass is between 1 to 2 times 10 to the 12 solar masses, the total mass. Let's say maybe 10 giga years ago, I don't know, maybe it was 10 to the 11 solar masses. So 1% of the today's mass. And then maybe you accrete your stream, your parent dwarf galaxy, the parent dwarf galaxy of LMS-1 with some mass, and you also have the distribution of gas. You let that system evolve, and then meanwhile, and then maybe one of the ways would be to study that and then you have a control simulation where you do not accrete any system, and you have a system where you do accrete a system, and then you let them evolve, and then you can say to some extent that how did this early accretion of LMS-1 distributed the gas, and how it compares with where there was no accretion. So I know that there have been such studies done, not with respect to LMS-1, but just that how the accretion of dwarf galaxies can affect the gaseous distribution in the Milky Way. I'm not sure about citations. It's just coming from the fact that I've heard other people's presentation. But what I can say is that for the Sagittarius stream, where is Sagittarius? For Sagittarius stream, I particularly know, and maybe already know of this understanding, that what we think is that the Sagittarius stream, it recently perturbed the disk. So the Sagittarius dwarf galaxy that sits somewhere over here, it went through the disk, and that has perturbed the disk. And this perturbation is what was noted as the phase space spirals in the Gaia data. So we know that such massive streams such as Sagittarius can perturb at least the stars in the disk. So if they can perturb the stars in the disk, they can potentially also perturb the gas in the disk.
Yeah,
but I'm not particularly sure about any particular study, any particular paper that has addressed this with respect to Sagittarius or any other stream.
Right, on these potential correlations, right? Okay.
Yes.
Yeah, of course, for the modeling, yes, this is a very interesting possibility. Yeah. Thank you so much.
Welcome, you're welcome.
Next question by Maria. Please, Maria.
Okay, thank you. Thank you for your presentation. It was really nice. I have a question that is very general. You mentioned that when you use your algorithm, the stream finder, you use models for the orbits, right?
Right.
Is it possible to make the opposite, like to correct the model using the data?
Definitely, yes. Is that all question, or this?
That's the question, because
okay.
I find it really interesting. This.
No, definitely. So one of the ideas, I mean, once we saw that the stream finder thing is working, that it's detecting stream, then one of the things we immediately started to wonder. So Rodrigo, Nicola, and I, along with other collaborators, was also. So here we are assuming some galactic potential model that is close to reality, and that's the reason. The fact that it's the assumed galactic potential is not very wrong is the reason why we are finding streams. Had our galactic potential model been very wrong, then the integrated orbits would be wrong, and then we would have not been able to find any of the streams, right? So what we can do is that, I mean, within Stream Finder, what we can do is that we can iterate over different galactic potential models, or we can iterate over the parameter of different galactic potential model. And that model that maximizes the stream detection, or maximizes the stellar density in the streams, or maximizes the number of stream detection, can then be assumed as the best galactic potential model. Do you see my point there?
Yes, yes.
Right. So, I mean, in principle, that can be done. But then again, I mean, Stream Finder, at its present stage, it's computationally very expensive. So we are running, I mean, thousands, millions of CPUs using thousands of millions of CPU hours to basically process the Gaia data just once. So then that would mean probably years of work to maybe do that in the way. But then again, I mean, maybe once we have these stream detections, what we can do is then just concentrate on these detected streams and try and maximize their signal to constrain the galactic potential. Maybe your question was related to this answer.
Yes, exactly. Yes, because I was thinking like not maybe it's not practical at let's say in the practice, but in the theory it's like well sounds great because you can use this because of course you have other data to confront to see if it's really a stream or not, and then you can use this to fix the this little difference between the models in the orbits. So,
or one of the other things we can do is that now we have these streams, we can just use these streams and try and find the best potential model using these streams, using the phase space distribution. So basically use these streams, integrate orbits and different galactic potential model, get the best model, and then run stream finder again using this model, then get more streams, and then basically iterate this process, right? I mean, that's another way to go about this.
Exactly, yes. I was thinking about this. Thank you.
Thank you.
And I have a last question, Khyati. How long does a string survive? At least an estimate. It survives detectable when it starts its orbit around the... I know it must depend on a lot of parameters on the orbit, but some rough estimate.
Yes, so I mean, like you said, that it depends on lots of parameters. I mean, it also depends if the stream is close to the bar, the rotating bar, because bar can perturb the stream, or if it's in the outer halo where the stream would survive for a longer period of time because there's no disturbance from the bar or from the disk. But I would say, I mean, for a stream to be detectable, for a low mass stream, like a globular cluster stream to be detectable, I'd say that probably at least more than, I mean, 8 gigayears or so. If it's within 8 gigayears and it's not perturbed too much by anything, then maybe 8 or even 12 gigayears for that matter it's possible. So there are these. So Raymond Carlberg from University of Toronto, he runs these simulations in a very cosmological context. And so he has globular clusters inside dark matter subhalos, and then he accretes these systems onto a Milky Way-like potential. So it's a full n-body simulation. And then what he's showing that even if you start a simulation 10 gigayears ago, 12 gigayears ago, you can still find streams. But then again, it depends on the orbit on which you are. So in principle, you can detect a stream even if it's 12 dynamical gigayears old, or you can even lose a stream within 1 gigayear if it's too close to the bar, for example, or it's perturbed by something else. So I know I have not answered your question because I practically said what you asked. But yes.
Thanks.
Yeah.
What's the order of magnitude, the number of stars that you see in these streams you detect in Gaia, in each stream?
In each stream, it really varies, but I'll say we get at least more than 200 to 300 stars per stream, given the magnitude limit of 19.5. So there is this photometry component in Gaia, which is the G magnitude. So the G of Gaia goes down to 21, but we make a cut at 19.5 just to be homogeneous in the data set. So until the magnitude of 19.5, we get around more than 200 to 300 stars on an average per stream. So for example, this stream that you're seeing here, GD1, that's going here and then continuing down to here, this has around 1,000 stars. This phlegathon stream that you're seeing here, it has around 500 to 600 stars, but then this stream over here, it has a few, like 100 or 150 stars, if I'm not mistaken. So, and then these very, very tiny streams like C15 over here, or C13, these have less, slightly less. But I'll say 300 to 400 is on an average.
Right. So I'd like to thank you again, Khyati, for the
Should I shut down the
presentation.
screen? Should
Yes,
I exit the screen? Okay.
I'd like to thank you, your time, you sharing your research and your knowledge.
It's a pleasure.
Thank you a lot, and I'd like to thank you, everyone present in Google Meet and YouTube. And that's it.
Thank you everyone. Have a nice day.
Thank you. It was a great talk.
Yes.
Thank you, Sylvia. Thank you. It was a pleasure to meet you all and be here. I truly wish I was there with you in person, but
Oh yeah, we'll see. Just wait for the pandemic calm down a little bit, and then we can try to invite you to our institute to work with our group also.
That
will be a pleasure.
The pleasure would be all mine.
Well, thank you. Thank you very much.
Have a nice day.
Thank you. Great week for you, for everybody.
Yeah,
bye.
Richard, we can finish the broadcast.
Bye-bye.
Bye, everyone.